Great pleasure to have Serena Dipierro from University of Western Australia. So Serena will talk about long-range phase transitions.
Thank you very much. So thanks, Stefania. And thanks to all the organizers. Yeah, it's a big honor for me to speak in this series of talks. So I want to talk about these phase transitions, and basically the talk is going to be in two parts, I would say. The first part, I will try to somehow describe the theory of phase transitions as Landau introduced, and that's basically we wrote in this recent survey with Enrico Valdinoci. And then in the second part, I will go to the more mathematical part, I would say, where I will discuss some results obtained in the setting of long-range phase transitions with mostly with Alberto Farina, Joachim Serra, and Enrico Valdinoci. So let's see. Okay, so this is just a picture of Landau when he got arrested. So the picture is here because, yes, I will try to describe the theory of phase transition as it was introduced by Landau. And so basically the phase transition or phase coexistence, as I think physicists used to call it, is something that we are used to experience in many situations, for instance, mostly in situations of melting, freezing, vaporization, and condensation. But I think it became really popular when people looked at the changes of state in superconductors, so from the state of conducting to a superconducting state. And so basically, a common trait in the study of phase transition is I want to describe a given system in terms of some relevant physical quantities that can be temperature, pressure, volume, anything. And I will mostly focus on temperature in what follows. And so basically the idea is that so I have this system that I want to describe, and I associate to the system some sort of energy, and the energy will be some sort of ability to perform some task. But then, of course, sometimes the system may waste some energy in the form of heat, the so-called latent heat. And so I will call the free energy, and that's the energy that I will look at, the difference between the full internal energy of the system once I remove, and then minus the energy that is unavailable to perform some work because it gets somehow lost, released in the form of latent heat. And the minimizers of this energy, or more stable one, more generally one can look at stable critical points, they are observable states of our system. And so the idea is that, for instance, if you vary some physical parameter, again, I will focus on temperature, different phases of in your system may occur, and typically, basically, what happens is that you have a disorder phase which corresponds to high temperature, and then once you decrease the temperature, somehow the system gets well organized, and then you go to low temperatures where you have a system that is again well organized. For instance, if you think about magnetization, there is a critical temperature that is the Curie temperature, above which basically magnetic materials do not have permanent magnetic moment, while below this critical temperature, somehow the atoms align themselves and behave like tiny magnets, so that at this point, at this temperature, the magnetic material shows a permanent magnetization oriented in a certain direction. And of course, this happens in a way, so the way it happens is that the system produces some sort of supplementary interfacial energy because there is a creation of, because of this, so the atoms gets aligned, and I have the formation of magnetic domains, and I have this sort of interface between these magnetic domains, which of course favors domain segregation, and I want the phase separation, so the interface between different phases, to be as small as possible. And so to model this phenomenon, to put it into a mathematical setting, one can consider an ordered part. So first of all, one fixes, in general, a notion of phase that can be magnetization or, again, different states of a given material, solid or liquid or something like that. So you fix a notion of a phase, and then you consider an ordered parameter, which I will call eta for the first part of the talk. And that's how physicists used to call this parameter. And then I will switch to U, which is the way we usually denote functions. And so this order parameter for me describes how every point of the system is organized according to this given notion of phase that I have defined. And yeah, it can be, so for me, this parameter is going to be a scalar function. So it is called a parameter. It's actually not a parameter. I mean, it's a function in the end. A scalar, for me, it can also be a vector, a tensor in more complicated situations, but for me, it's going to be a scalar. And so what Landau did, so Landau looked basically at the free energy in a stellar expansion to be something like this. So you have some parameters, A0, A1, and so on, that depend on physical quantities. And for me, this physical quantity is going to be just the temperature. So all these parameters, all these AI depend on temperature. And then I have this expansion here. And so basically, Landau constructed two models for phase transitions, depending on whether there is some latent heat is produced or not. Okay, and for us, this is going to be, so for people in PDE, this is going to be a little bit confusing because Landau calls, so defines to phase transition to be second order and first order, which is a bit confusing for us because for us, the order describes the order of the equation, while here this is going to be related to the presence or not of latent heat. And we will see why he calls first order and second order. And so the second order theory of phase transitions basically involves no latent heat. So there is there's no heat that is produced or released during the change of phase without changing the temperature. And so in this case, up to higher order terms, the energy is something like this. So I have A0 plus A2 eta squared plus A4 eta to the power 4. So this is symmetric with respect to the order parameter. And yes, so there are some assumptions to describe the formation of new phases when I cross some sort of critical temperature, which will be this Tc for me. And in this way, one can check that the critical points, if you see, of the free energy, and I will have a picture, and these are, if I am above the critical temperature, just 0. If I have below, I produce 2 more critical points. So I have 0 and 2 more critical points. And yes, so let's give a look at the picture, because so the blue line here is when I am above the critical temperature, and then I start decreasing the critical temperature, and at some point I produce basically also these two are the minima, and then at some point when I have below, I have basically these two non-degenerate minima, which somehow represents the 2 different phases of the material. And yes, so this is the bifurcation diagram. If I am above the critical temperature just at 0, and then I have 2 branches of critical points. And this is the description of the energy as a function of the temperature, and this is the first derivative. So if you see the first derivative, so the second derivative has a jump here at some point, and that's why this is called second order theory of phase transition, because it's the second derivative at the critical temperature that has a jump. So when I am here below the critical temperature, I have 2 different phases that coexist. While in the first order theory of phase transition, where basically I have some latent heat, which is somehow released or supplied to the medium without changing the temperature. So let's look at the energy. So the energy that Landau describes is something like this. So I have these parameters, eta squared, and then plus the second parameter, eta to the power 3, and so on. with some sort of conditions that describe what happens at the critical temperature. And the picture now is like this. So I have 0 here. And then when I decrease the temperature, so at some point I have basically 0 plus another state, another phase, sorry, another minimum, which means I have coexistence of two phases. When I go below, I just have this one. And yeah, I think, and this is the graph describing, the diagram describing the derivative of the energy with respect to temperature, and you see you have discontinuity here already. So that's why it is called first order, because this is related to the jump in the first derivative, while second order is related to the jump in second derivative. And so basically, both these models present a situation in which I have two stable states that coexist. And so for the second order, when I am below the critical temperature, and for the first order, when I am at the critical temperature. And so what I want to understand is how these two different phases coexist, and if possible, I want to describe the geometry of the domains corresponding to each phase. I want to describe the interface. So in principle, if we just say, okay, so the system wants to be in the situation in which I have the pure phases, any configuration in which any point of the state lies in any of the two phases is as good as any other. But this is not actually what we experience in, maybe not in our life, but in sometimes maybe in our life, but in experiments, because what we experience is that the change of phase actually occurs in very specific regions. So for instance, if you look at this picture, so here basically I have this silicon steel that is immersed in an external magnetic field that gets activated at some point, and you see that I have two different magnetic domains, the maybe white one and the dark one, and you see that the separation is pretty neat. It's not something random. It's pretty, I have pretty straight line. So there must be something else, and so basically the idea is that you don't just look at a term in your energy that only favors the formation of, so that only favors the two pure phases. You want to add something else that somehow penalizes the abrupt change of phase. And so what you look at the energy, an interaction energy of this form. So here I have a double integral of eta of x minus eta of y squared times some given kernel that we will describe. And so this one here, so this term here should somehow penalize the fact that eta of x and eta of y are two values. So I want somehow to avoid to have unnecessary interfaces between the two phases. And so one can also assume the kernel K to be symmetric under translations and rotations. And so my kernel, this kernel calligraphic K will be actually a K of the distance between x and y. And so if the kernel is short range, so x and y do not interact if they are sufficiently far away, say for distance bigger than some rho for some small rho, and of course you can do your computation here, and basically the interaction term is well approximated by the integral of the gradient square. And so for short range interactions where basically you only allow points that are close by to interact, one can describe the coexistence of the two phases for both the models, first order at the critical temperature and second order below the critical temperature, via this energy functional where you have this integral of the gradient square that penalizes the formation of unnecessary interfaces, plus the integral of a potential, which is the classical double When potential with same minima at -1 and 1. So -1 and 1 will be the two pure phases, and so this W would favor the formation, would favor some of the system to be in these pure phases. And so And so in this situation, the phase separation between, so the separation between the two pure phases is dictated by the usual surface tension, which basically tries to make the interface a codimension one surface with the least possible n-1 dimensional area. And so, for instance, this is, I think, the typical trick I mean, for this model. So if you introduce a small parameter and you look at this rescaled energy function, well, basically, I'm looking at this term as some sort of penalization, some sort of, so I want this one to be the dominating one in the end. And this is a sort of penalization that penalizes the formation of phases. So if I do like Cauchy-Schwarz and then coarea formula, I can bound this quantity with this object here. And so what I try to do, what my system tries to do, it tries to be in a situation in which this area here is as minimal as possible. And so energy minimizers try to optimize the lower bound and try to sit on the zeros of the double well potential as much as possible. And so for small epsilon, the minimal energy is expected to be related actually to the area of the boundary of E, where E now for me is the set in which the order parameter is basically equal to +1, where in the complement it is equal to -1. And this can be put into a rigorous mathematical setting, and there is a famous gamma convergence result that is due to Modica and Mortola, where they basically prove that if you look at the energy suitably rescaled, gamma converges essentially to the perimeter function. And so minimizers try to converge to characteristic function of a given set that describes the separation. If instead you allow for long-range interactions, so you allow points that are far away also to speak with each other, then you cannot approximate your energy with the gradient, the gradient term. And so the energy is at this point described by basically the same potential term, so the double well potential that favors the formation of the two pure phases. And then I have some sort of double integral here with a kernel. And here, this double integral is to be computed on this sort of weird domain that, so this notation should stand for this cross-shaped set, which is basically, so basically the idea is that you don't want to, so if you're looking at what happens in a given domain, you don't care about the interactions outside. So you care only about interactions of points that are inside, meaning that you keep in the energy every interaction between x and y, where at least one of the 2 points is in omega. So you have omega times omega, and then you also have the complement times omega, and then omega times the complement. So the only interaction that you forget is the complement of omega with the complement of omega. Okay, yes, so this is what I was mentioning. Okay, so special cases of kernels are the ones that are homogeneous of some degree D. And basically, if you want your energy to be finite, you do your computation, you end up with a restriction on the degree. And so one needs D to be in n-2 minus n. And so we will look at situations in which D is -n minus 2s with now s in 0, 1. And this covers basically this domain. And this is the kernel basically of the fractional Laplacian that will appear at some point. And so in this situation, what happens is that the limit interfaces are now again related to minimizers of some perimeter, but of the classical perimeter if this parameter s is above 1/2, and of a non-local perimeter when s is below 1/2. So somehow the situation localizes and is more similar to the classical case when S is above 1/2, while the non-local structure of the problems is preserved when S is below 1/2. Yes, so, and again, also this fact can be put into a rigorous mathematical setting, and there is a proof of gamma convergence that has been obtained by Ovidiu Savin and Ennio De Giorgi. Okay, so I'm going to look at this point at the specific program that we looked at. And so this is the fractional Laplacian, which is the operator associated with the energy, with the kernel here, which is 1/y m plus 2s. And S, so is in between 0 and 1, as we said before. And I will look at the non-local Alenkane equation. So I will make a, so here I can make a choice of double well potential W to have, and this is I would say maybe the most famous choice that you can make. So this is the Alenkane equation. Yes, so as I mentioned before, if I look at minimal solutions of the equation and I take a blow down, then they converges to the characteristic function of a set E, where E is a local minimizer of the classical perimeter if I am above 1/2, and the fractional perimeter when S is below 1/2. And this is the result by Ovidiu and Enrico that I was mentioning. And so let me just tell you what the fractional perimeter is briefly. So the fractional perimeter is defined when S is in between 0 and 1/2, and I have the same kernel of the fractional Laplacian here. And what I do, basically, I look at interactions between disjoint sets as a double integral of this kernel. And then the fractional perimeter basically counts the interactions of the set E with the complement with respect to some reference domain. So you have a reference domain, you have your domain E, and the perimeter sees the weighted interactions of the set and the complement, so weighted by this kernel. And so this is this is the objects that one has to try to understand if one wants to somehow. So let's put it this way: the regularity theory of non-local minimal surfaces, objects that minimize this non-local perimeter, is related to the regularity, so the geometry of the interface of between two faces in the long range phase coexistence model. And yeah, let me skip this part. So what we looked at some time ago, together with Joachim Serra and Enrico Valdinoci, is actually a more general situation in which we have an operator of this type, and this is exactly what was written before for the fractional Laplacian, where you also add some sort of anisotropy here. So you have a function of the direction. And we looked at what we call the genuinely non-local case, which means that I will fix a parameter below 1/2. So I really want to look at the situation in which, in the limit, I see non-local minimal surface, in which the non-local structure of the problem is preserved when I look closer and closer to the interface. And so, okay, if you're too bothered by this anisotropy, just think about the fractional Laplacian. So if I take mu to be just 1, this is the fractional Laplacian, and whatever I'm going to say is true and then holds true and is new even in the case of the fractional Laplacian. But you will also consider more general anisotropic operators here. And in reality, so I think the reason why we also wanted to do it for a more general situation is because somehow the proofs of the result that I'm going to present are very geometric somehow. So once you understand the situation of the fractional Laplacian, it's not too difficult to frame it into a setting of anisotropic geometry. Okay, once you replace balls with standard balls with the balls related to the anisotropic operator. So that's why we actually dealt with this more general situation, with actually no major issues, I would say, from the philosophical point of view. And so this is for the operator. For the right-hand side, yeah, you can consider the Alenkane equation, so where the nonlinearities of the type u minus u cube, you can consider more general nonlinearities. The important thing is that you want some sort of monotonic regime here. So you want this f to be decreasing when I am close to the two pure phases, when I am close to -1 and close to +1. And this is why here at some point I want to apply some sort of maximum principles when I live in this area here. So that's why I need some sort of let's say monotone properties. And so yes, so this is the typical example is take f of u to be u minus u cubed. That's the classical Alenkane equation. And this is the more general setting that we are in. So we have L of u equal to f of u, and this is the equation that I'm looking at. And I will introduce this notation. So I will call, so for me, the interface of the solution u will be this set here, where u is, so the absolute value of u is smaller than 1 minus k. When I have sufficiently far, basically from -1 and +1, so this is for me the interface. And I'm going to define this notion of being gamma trapped in BR in some direction omega. So omega is a vector, gamma and r are positive parameters. And I would say the interface is gamma trapped in a ball in direction omega, if this happens. And this is a bit ugly to see, but the picture I think is more clear. So I have a ball, and I'm looking at a slab of with to gamma in a given direction omega, and I say that u is gamma trapped in BR if the interface is contained in this slab. Now, of course, if gamma is larger than r, I'm not saying actually anything, but if gamma is significantly smaller than r, this is an information. So it's a good information to use. Okay, and then let me give this definition, because this is the problem that I want to look at. So I say that u is one-dimensional if I can find the u0 and the direction such that u is equal to u0 of omega dot x, for any x. And the reason why I'm introducing the notation is because I want to look at this conjecture that Ennio De Giorgi posed in 1978 for classical Alenkane equation. So this conjecture says that if I have a bounded and smooth solutions of the classical Alenkane equation in a Rn, and the solution is monotone in a given direction, strictly monotone in a given direction, then u is one-dimensional, at least if n is smaller than or equal to 8. Okay, so so this was posed by De Giorgi, and yeah, so it is somehow, so the reason why he puts, so he put this restriction on the dimension is because, as we mentioned, there is this result that relates let's say the interface, so the level sets of the solutions with minimal surfaces, basically. And so basically, the idea is that De Giorgi knew the regularity of minimal surfaces, and he thought, of course, somehow this problem has to be related to that regularity, and that regularity is available only up to some dimension. And so there must be some sort of bound here on the dimension. Otherwise, you can construct a counterexample, and this is what actually happened. So this result is true as it was stated by De Giorgi, so with the bound and the dimension, and it was proved as it is stated here in dimension 2 and 3 by Ambrosio, Cabret, Gussu, Bengui, and also Caffarelli, Berestiki, and Nierberg. From dimension 4 to dimension 8, there is a paper by Ovidius Saviens, I think that's the Ovidius PhD thesis, with the additional assumption that the limit at plus and minus infinity are equal to plus and minus 1. And then there is a counterexample that is due to the Pino-Kowalczyk way in higher dimension 9 and higher. So the result is stated by De Giorgi is true as it is with this bound on the dimension. And so basically what we want to try to do, we want to understand the non-local setting. So again, the regularity, so the regularity of level sets of solutions are related to classical minima, so to the regularity of classical minima surfaces when I have above 1/2 and non-local minima surface when I am below. So in this situation, in the regime that I'm considering, so I'm assuming S below 1/2, so they have to be related to the regularity of non-local minima surfaces. And so the result that we obtain, so we call this theorem 1, with Joachim and Enrico, is that, okay, I have a solution of my equation. I assume that my interface is trapped in BR with gamma to be equal to some function AR times R, where this function AR goes to 0 in some direction omega R. So I am some sort of flatness at infinity. And then my solution is 1D. So there is no, this is very geometric statement in a sense, and there is no restriction on the dimension here, because the restriction on the dimension is somehow hidden in this condition here. So this is true when non-local minima surfaces are good enough somehow, at least for our proof. And I think it's a very nice and strong result, because, for instance, it's not true in the classical case. It's not true that if you can trap the interface of a solution of the classical Alenkane equation in this way, then the solution is 1D. And the reason is because, for instance, there's this paper by Del Pino-Kowalczyk way, where basically they constructed, starting from the catenoid, they constructed basically solutions of the Alenkane equation modeled on the distance to the catenoid. So they will go towards -1 outside here and then towards +1. And the catenoid here has logarithmic growth. So if you look at this condition, AR in that case would be something like log R divided by R, which goes to 0. And the interface is gamma trapped, but clearly that solution is not one-dimensional. So that is not true in the classical setting. Yeah, let me skip this. And then, so theorem 2, again with Joachim. So what we, so if we put it more into the setting of the conjecture by De Giorgi, you have a solution of the Alenkane equation with a fractional Laplacian that is strictly monotone in one direction, and we assume the limit to be plus and minus 1 at infinity. If n is smaller than or equal to 8 and s is sufficiently close to 1/2, then U is 1D. So here we have this bound on the dimension, and we say S sufficiently close to 1/2. And as I hope I will have some time to discuss this, this is related to the fact that this is a range where basically the non-local minima surfaces are known to be regular. And this Sn is not known. I mean, it depends on the dimension, but we cannot say what this Sn is. We can just say, okay, if S is sufficiently close to 1/2, so if we can find some Sn such that when S is above, and then the theory is true when S is above this Sn, but we cannot quantify. And this comes, as I said, from the fact that it's not known, this Sn is not known for the regularity of non-local minima surface. But I will come back to this later. And in dimension 3, we can actually state the Giorgi conjecture basically as it is, so without the additional condition on the limit at infinity. If you have a solution of the fractional Alenkane equation in dimension 3 that is strictly monotone in one direction, then U is one dimension. And yeah, let me just put things into a context. So the conjecture so the Giorgi conjecture in the fractional setting is true. So this is the state of the art. So it is true in dimension 2. So this was proved some years ago by Cabré and Sola-Morales when S is equal to 1/2. And then for any S, some years later, there are two different proofs, one by Yannick Cyr and Enrico Valdinoci, and one by Chai Cabré and Yannick Cyr. In dimension 3, there is a proof that is due to Cabré and Cinti when S is equal to 1/2, and then when S is above 1/2. And so basically, we fill this gap here in dimension 3. So now when S is below 1/2, this is also known thanks to the result with Alberto and Enrico. And then there is one result in dimension 4 and S equal to 1/2 that is due to Alessio Figalli and Joachim Serra. And that is basically all that is known. So we don't know how to go to n equal to 4 for any S and higher dimension. I think they strongly use the fact that basically once you go to the extension, you deal with the reaction diffusion equation with the Laplacian, and not with the more general local operator in this paper. So they couldn't do it for any S. When you also assume the limit at infinity, so if you assume that the limit at infinity is equal to plus or minus 1 uniformly, this is known to be, this is called Gibbon's conjecture, and is somehow related to problems in cosmology, because you want to know that basically some physical laws only depend on time and not on space. And so in this case, the solution is one-dimensional for any n. So the fact that you have a uniform limit basically kills the assumption on the dimension. When you don't have the uniform assumption, this is the result that I said. So when n is below 8 and S is very close to 1/2, and you assume the limit, then the solution is one dimension. This is the result with Joachim and Enrico. And then when S is above 1/2, there are actually two papers here. I put everything together, but there are two papers that are due to a video showing. One was when S is equal to 1/2, and the other one was when S is above 1/2. So up to dimension 8, again, with the limit assumption. Okay, so I'll try to show you maybe the proof of the main results. Okay, so there is a theorem 0 that I won't linger too much on this. This is really the basis of the improved, so the basis to prove our geometric theorem. Basically, without going too much into the technical details of the notation, if you know that some trapping condition holds so up to B1, then trapping condition also for in B1 also. So you can somehow improve your trapping, and the picture is somehow like this. Okay, the picture is not precise because possibly you can vary the direction a bit, but it gets stabilized at some point. So basically you can improve the trapping. And this is what I call theorem 0. Okay, so and this is the general strategy. So you have a general trapping result, which is theorem 0. Then you can prove flatness from infinity. And so because this general trapping tells you somehow something about the structure of the interface and allows you to do some sort of sliding methods from infinity. And then you have the De Giorgi type results. So then the solution is one-dimensional if the monotone assumption is true. So let me try to maybe briefly give you an idea about the proof. So I will start with the last theorem, the theorem of proof the proof of theorem 3. Theorem 3 is the one in dimension 3. So if you have a monotone solution of the Alenkane equation, then it is one-dimensional. Here, so dimension 3 is good in a sense because we have a lot of information about dimension 2. So the conjecture is proved even for stable solutions in dimension 2. So we can use those results. And I will show you how. So first of all, we look at, so we exploit extension methods. So we don't want to do computations. We don't want to compare energies in basically on the trace. We don't want to compare the non-local energies. So what we do, we go to the extension. So, and I will call so x, z points in a range times 0 plus infinity. So x lives downstairs, and then I'm adding one direction, that is z. And yeah, this b plus r is the ball, so the cylinder. So the ball downstairs times 0r, and I have the Poisson kernel. So given a function v, I can define the extension of this function adding one variable. And then basically one can check that essentially the minimization is preserved if I do this. So if I look at the, you see the calligraphic F is the non-local energy. I mean, I don't like it a lot if I have to compare energies of competitors, because I have a lot of terms that I have to deal with. While if I add one more variable, I can look at an extended. I can look at this local energy now. Here I have a weighted gradient square, which I like more. And basically, the minimization procedure, the minimization is preserved. So if I have, so let's say the extension is an extended local minimizer if and only if V is a local minimizer downstairs. So I'm going to look at minimizers in the extension, and I will be fine downstairs. And so this is what I was mentioning in the beginning. So I can define, so I have this monotone condition on the derivative with respect to x3. So I can well define u sub r, sorry, u sub r and u bar to be, so u sub r is the limit when x3 goes to minus infinity of u, and u bar is the limit when x3 goes to plus infinity. And now these are two-dimensional objects, two-dimensional functions, and somehow, so what I know about my solution u is that it is monotone in one direction. So this implies some notion of stability with respect to the second variation of the energy. And the stability is a good condition because it gets preserved when I pass to the profiles at infinity. And so I have basically two stable solutions in dimension 2. And now I can use results from dimension 2 for stable solutions, and I know that the profile is one-dimensional. So this is important. And this is basically the reason why this proof works well in dimension 3, because we can use information from dimension 2. We know that the conjecture is true for stable solutions, so we can use it. And so they are 1D, and they are also minimal solutions. And now I want to somehow pass this information on minimality from infinity to, so from the profiles at infinity to my solution. And here there's a trick. There's a nice paper due to Jerison and Monod that basically, this is a bit of an esoteric picture. So I have basically, so the idea is I want to compare energies, okay? So, and I'm doing it in the extension, so I'm happy because I have the gradient square. And the idea is, okay, I have my, so this is E of U, I have my solution, I perturb it a bit. These two green dashed lines are the two profiles at infinity. And then I basically look at gamma, which is whatever is in between the two profiles at infinity, and alpha and beta are taken care of by the profiles at infinity. So the bottom line is that I can somehow have, in all these regimes, I have some sort of order in terms of the energies. And once I put everything together, the energy of the perturbation is above the energy of U, of the extension. And so the extension of U is a minimizer, and so U is also a minimizer. And now I like this because now I can take the blow up because U is minimal, I can exploit the convergence of U epsilon to the characteristic function of E. And I also know that the level set of U epsilon approaches the boundary of E with E now that is the fractional minimal surface in R3. And then I know by a Bernstein type result in R3 that E has to be the half plane. And so basically, I know that I have some source. I am very close to the half plane, going back to U epsilon. So I have this trapping condition at infinity remember, with the function AR. And so I can use theorem 1 to say that U is one dimension. So essentially here I need to do a bit of work to prove that the solution is minimal. And I use a lot the fact that I have information, I have pieces of information from dimension 2. And then I need to know somehow to use theorem 1, to use the geometric result, I need to know the regularity of the minimal surface that I'm looking at, which is true thanks to a Bernstein type result. So these are basically the two points. And then basically theorem 2, the one in any dimension up to 8, where I also assume the limit, follows essentially the same line. It's shorter because monotonicity plus the limit at infinity gives me that U is a minimizer, so I can do this blow up, and I converge, and then, okay, n equals to 3, that was already done, but when n is below 8 and S is large enough, I have a result by Caffarelli and Valdinoci that tells me that non-local minimal surfaces are as regular as classical minimal surfaces, somehow they inherit the regularity from S equal to 1/2. And so they are regular in this setting. And so E has to be the half space. And then I go back to U epsilon, the interface is gamma trapped, and then I can apply theorem 1 to prove that U is one dimensional. So I don't think I have a lot of time to go to the proof of the geometric result, but I guess one point that I want to make is that the reason why I think is somehow a powerful result is because you see this last step here is for free if you know the regularity of non-local minimal surface, which unfortunately is not known in any dimension. But if you know that, then basically this last step is for free. So once you know regularity of non-local minimal surfaces, you can use this geometric theorem to prove the fractional De Giorgi conjecture in this setting. And I think I'm gonna stop here, and thank you for your attention. And
thank you very much, Serena. Thank you. Very beautiful talk. Is there any question for Serena?
Okay, so may I ask a question?
yeah.
Okay, so I remember your result set is when the S is very close to 1/2, then you have the similar result,
Yes.
like already proved before.
Yes.
Right. Okay.
Yeah, this one here.
Right. But is there any known like counterexample when the dimension is bigger than 8 or when it is away from 1/2?
So when n is bigger than 8, unfortunately, not much is known for. So you said when S is below 1/2 or bigger than 1/2?
Yeah, when S is, say, it's away from 1/2, because here what you mentioned is it's very close.
Yeah. So
to 1/2, right?
S is below 1/2. So I don't think. I don't think the geometric result is true when S is above 1/2.
Okay.
When n is bigger than 8, okay. So so let me put it this way. I don't know actually what people expect. So you would expect to have some sort of constraint on the dimension, like in the classical conjecture by De Giorgi.
Okay.
It's not. I don't know if people would expect this constraint to be the same. So dimension 8.
I see.
So there are some results for non-local minimal surfaces, so I would say this is strictly linked to the regularity of non-local minimal surfaces. And I think there is a result that is due to Davila del Pino way, where they prove that when S is very close to 0, so you are in a very strongly non-local regime, then Lawson's cones are stable, I think, not minimizer, but stable, in dimension 7, I think. So which means, if they are not minimizer, fine, this would not somehow disprove would not give us a different setting. But if, for instance, if they are also minimizer, this would tell us that somehow the regularity theory for non-local minimal surface when S is close to 0 breaks already in dimension 7 and not in dimension 8, like for classical. And this may have some sort of this may reflect into the setting of into this setting here of Alencano.
Okay, I see. Thank you.
And Serena, since you're on this page, this SN you said is not explicit. This
it's not explicit. This comes from the paper by Luis and Enrico, because basically I think they do it by contradiction. So it comes from compactness. So you assume by contradiction, and then okay, no. So there exists an SN such a in dimension 2 where you know that the local minimal surfaces are regular, then SN is 0, so you can go up to 0. But in general, it's not known. I don't think they even have a bound or anything, so it's not known.
Okay. And this is
so it
also
comes
for
exactly from their result. So this SN is exactly the SN of their result.
And for the anisotropic energy, still you have which results do you have?
So we have the geometric result. We have what we call theorem 0. So you have the geometric result. Okay, so to put it into the framework of the Giorgi conjecture, you may need some work to prove that so minimizers converge to minimizers of some sort probably of an isotropic perimeter. I think Monica Ludwig has some papers where she describes, so she introduces some versions of non-local anisotropic perimeter, I think. And yeah, perhaps one should try to look at that. Yeah, so we cannot prove the Giorgi conjecture for the more general operator because we rely a lot on this type of results. Yeah.
Thank you. Is there any other question for Serena? Okay, so if no more questions, so let's thank Serena again.
Thank you very much.
Thank you, Serena, for the beautiful talk.
Yeah, thanks for the nice talk.
Yes.
Thank you very much for inviting me.
Yeah, everything's very clear.
Yes, it was very nice and very clear.
Thanks, Serena.
Thank you, Koan.